Okay, so let's continue with formulating the different types of Laplace transform for different types of functions. So now we are going to look at f of t. F of t is equals to an exponential function, e to the power at. So now we want to find the Laplace transform. We're going to find the Laplace transform of e to the power at. Obviously, a is a constant. So we are saying where a is a real constant, that is not equals to 0. So this is very important. A is a real constant and is not equals to 0. So if you want to find the Laplace transform of this exponential, the general formula for this exponential, so it's going to be the integral from 0 to infinity e minus st multiplied by f of t, which is now e at, right, dt. So we can rewrite this as so the laws of exponential. So same base, you add the powers, so I can rewrite this as s minus a t dt. So now you want to integrate an exponential. So if you integrate this, you are going to have s minus a t over the derivative of the power, which is s minus a, right? And then from infinity to 0, because we have to include the limit from infinity to 0. So okay, then now you substitute the limit. So if you substitute this one, obviously if you start with infinity, this is going to be 0, right? So we are going to have so if you substitute this one, you're going to have 0 minus 1 over minus s minus a, isn't it? Because if you substitute 0 where there is t here, you substitute 0, you're going to get e to the power 0. We know that anything to the power 0 is 1, so that's why you're getting this one here. And then this simplifies to 1 over s minus a. So now we know that the Laplace of e at is equals to 1 over s minus a, right? Also, this one is very important. You have to remember this one, because we'll be applying this different types of Laplace transform when you're solving problems. And earlier I mentioned the Laplace when you have f of t is equals to 1, then the Laplace of 1 we said is equals to 1 over s, right? But then what about let's say now f of t is equals to a constant, let's just say a constant k, right? So what is the Laplace transform of k, where k is a constant, it's a real constant? So this is the same thing as the Laplace of 1 times k, right? Same thing as the Laplace of 1 times k, and we can factor out k. So k times the Laplace of 1. So this will be k times the Laplace of 1 is what? Is this, right? So this is going to be 1 over s, which means it's k over s. So now, just for if you have f of t is equals to 7, probably you want to find the Laplace of a constant 7. So the Laplace of 7 is k, so this is going to be 7 over s. So basically this is the more general form of representing the Laplace of a constant k. Okay, so now just look at the Now let's look at trigonometric function. So you're gonna find the Laplace of a trigonometric function. So let's say f of t is equals to cos 80. Again, a is a real constant that is not equals to 0. So we're gonna find the Laplace of cos of a t, right? So again, we use e minus a s t times f of t, which now is cos a t dt, integrating with respect to t. So now we have two functions here. We have an exponential and a trigonometric function, and we're going to find the integral. If you remember from your past calculus classes, especially integration techniques, if you integrate e to the power a, x cos bx dx. If you integrate this, remember that you have this is equals to, I won't derive this, but you have to know how to. This is the general form of integrating an exponential, the product of an exponential and a trigonometric function, especially when it's cos. This is equals to b square. Oh, sorry, this is okay. Dx. This is going to be b plus then a sine. It's going to be a sine bx minus a sine bx minus, no, this is going to be b sine bx minus a cos ax, obviously, plus c. This is an indefinite integral, so we need to remember this. So that's what you're going to apply here when you're integrating the product of an exponential with the trigonometric function. So the integral of cos 80 dt, we are saying this is going to be this, so this is going to be e minus st over s squared plus a squared. If you forgot about this one, just go to the videos about integration techniques that I did for engineering mathematics 1. I think I did a video based on this, the different types of integration techniques. Go and remind yourself and see how you can apply this, how we get to this point. So we're just applying the integration technique here. So this is going to be a sine 80 minus s cos 80 from 0 to infinity. So that this is the integral. And then obviously when you substitute, so basically in order for you to get to this point, you just integrate by parts. Integrate by parts twice. You need to integrate by parts twice in order for you to get to this form. So that's what you did. You integrated this by part twice to get here. So once you're here, you just substitute now infinity, where there's two, substitute infinity. So your first substitution is going to be e minus s infinity over s squared plus a squared, a sine a infinity minus s cos a infinity, right? This is minus, and then you substitute 0, so e 0 over s squared plus a squared, a sine a 0 minus s cos a 0, right? And then, so now if you simplify this, obviously sine infinity, cos infinity, so you have a, this will be, so let's look at this one, infinity. So e to the power minus infinity, this will turn to 0, right? Which means 0 multiplied by this is what? It's 0. So this entire expression is going to be 0. So which means we're going to get 0, right? So 0 minus, and then you come back here, sine 0 is what? Is 0, cos 0 is 1. So here we'll be left with minus s, isn't it? So obviously e to the power 0 is what? It's 1, right? E to the power 0 is 1. So here you have 1 over s squared plus a squared times the minus s this side, right? And then if you further simplify this, we are going to get s over s squared plus a squared, right? S squared plus a squared. So now, which means the Laplace of cos a t, the Laplace of cos a t is equals to s over s plus a squared. So again, you need to remember this expression. The Laplace of a cos function is equals to s over s squared plus a squared. So the same thing, if you want to find the Laplace of sine 80, it's a slight, they have the same denominator, s squared plus a squared. It's just that now there's a slight twist for the sine function. It's just a slight twist. So now you're going to have a here. You're going to have a instead of s for the sine function. So it's still the same thing. Normally, for these, you need to remember this, and they are very important. Okay, sometimes instead of a, we can use omega instead of a. Let's just use omega. So this is going to be omega. Still, omega represents a constant, so this is going to be omega. This is going to be omega squared. Either way, a or omega, but for now let's use omega because I want to use a for hyperbolic functions. The constant a, I want to represent the constant is a for hyperbolic functions. For this trigonometric function, let's just use omega. Still the same thing. So here I can just say this is omega t, right? So we are looking for omega t, where omega is a real constant. Omega is a real constant. Okay. So where there's a is just omega. So this is how you derive for cos and then for sine. So now we have looked at the Laplace of 1, or the Laplace of k. We said this is k over s. The Laplace of t to the power n, and a polynomial. We said this is n factorial s n plus 1. The Laplace of an exponential function, we say this is 1 over s minus a, right? And then the Laplace of sine, or let me start with cos, of cos omega t. We are saying this is going to be of cos omega t s over s squared plus omega squared. and then the same thing with sine omega t. The denominator is the same. If you know one, you can find the other. If you know cos, you can find sine. So we are going to have omega. So these are the ones that we have done so far. So let's add on top of this one. So now I want to look at the for hyperbolic functions. Let's look for hyperbolic functions and see what we get for hyperbolic functions. Let's find the general expressions of the Laplace transforms for hyperbolic functions. So again, we want to find the Laplace. This is very simple. The Laplace of cosh AT, right, where A again is a real constant. So the Laplace of cosh. So remember that since this is a hyperbolic function, we can represent cosh AT. Cosh AT is the same thing as EAT, right? EAT plus E minus AT over 2, isn't it? And also sin AT is equals to EAT minus E to the power minus AT over 2. So this will make our lives very simple, because now the Laplace of cosh AT is equals to the Laplace of EAT over 2 plus E minus AT over 2, right? So now this, using the linearity property, we are going to get the Laplace of EAT plus half the Laplace of what? Of E minus AT. And we just did the Laplace transform of an exponential function. So this is going to be half. So this is going to be 1 over s minus a plus half. This is going to be 1 over s plus a, right? According to this one. So from here, now it's just a matter of simplifying this. So from here, you just collect like terms. So these are, you can factor out half, whatever way you use to combine these two functions, it's okay. You just factor out half, and then when you combine those functions, you're going to get s plus a minus s plus a over s minus a s plus a, right? So by intuition, you can see that this is a difference of 2 squares in the denominator. So this is equals to s minus a. So this is 2a over difference of 2 squares, s squared minus a squared. Then 2 will divide. So we have. So now we know that the Laplace transform of cosh AT, the Laplace transform of cosh AT is equals to a over s squared minus a squared, right? So again, if you know the Laplace transform of cosh, I think I did something. I made a mistake. Here. This is supposed to be, I'm sorry, this is plus, because this is plus, right? This is minus here, because this is minus on cross multiplying here. So I made a mistake. So this will be, okay, we're still getting half. Okay, let me just remove this. Okay, I'm sorry about that. So this is s, so this is going to be 2s cos a minus a is 0 to s over, then this difference of 2 squared, 2 squares like this. Okay, yeah, now it's perfect. And then this is equals to s over s squared minus a squared. So the Laplace transform of cosh is s over s squared minus a squared, isn't it? Which means, again, we are going to use, since the same principle that we use for the trigonometric functions, if it's sine, so now we are going to have a s squared minus a squared. But we can also prove this. We can also prove this the same way as we proved for cos. So if you know for cos, you can easily derive for sine. The same denominator, and then you just swap the numerator. For cos is s, then for sine is what? It's a. But we can also do it for sine. So the Laplace transform, let's just prove it real quick. The Laplace transform for sine at is equals to, remember we said sine, this is the this is how you represent sine. So half the Laplace transform of at minus at, right? And then this is going to be half, and then the Laplace transform of at is what? The Laplace transform of at is 1 over s minus a minus the Laplace transform of e to the power minus at is going to be 1 over s minus, now a is negative here, so it's minus a, right? And then this is half, this is 1 over s minus a minus 1 over s plus a, right? So if you combine these two functions, we are going to have s plus a minus s minus a, right, over s minus a s plus a, isn't it? And this is going to be half, this is going to be half, so we have so we're going to have 2a, the denominator, this is difference of 2 squares, obviously, difference of 2 squares, and then if you divide 2, then you have a over s squared minus a squared. So we come to the same conclusion, which is this. So now we've just added 2 into the list, cos a and sine a. Again, you need to remember this because we'll be applying this when you are solving equations, when you're doing equations and stuff like that. So now I want to touch something, a theorem. So I want to talk about a theorem. This is a very important theorem. So this is the theorem 1. So we call it the first shifting theorem. This is the first shifting theorem. S shifting, or you can call it the F shifting theorem. So it simply states that if f of t has a transform f of s, capital letter F of s, then e to the power a t times the f of t function has the transform f, capital letter F, s minus a. So let me write it. We are saying if f of t has a transform, f of t has supposed to have a transform, which is f of s, which is what we've been proving, right? And remember that in order for this, the existence and the uniqueness, so where s has to be greater than k, right? For some k, where k is a constant, for some k, this is, we have to note that we are saying if f of t has the transform, right, f of s, then e at, so So the product of the exponential AAT with that function has a transform. That is a transform. Now a new transform, which is f of s minus a. F of s minus a. So we can just represent this as the Laplace transform EAT f of t is equals to f s minus a. Okay, so let's go back a little bit. So remember we said the Laplace transform of f of t, right? The Laplace transform of f of t is equals to f of s, right? But now with the first shifting theorem, we are adding a new term to this one. We are adding a new term now, which is we are adding EAT. So now we are adding a here, which means it has to be reflected this side. So what are we going to do? So a is positive here. So this side we are going to have what? A is going to be negative. So s minus a, like this, right? As the power a is positive here, it's 18. As the power is positive, so here is going to be negative. That's how we are going to deduce the first shifting theorem. This is just the first shifting theorem. We are shifting the function by a, right? A, which is a real constant, isn't it? So I think in order for me just to illustrate this, I need to jump on into an example. Let's try to do an example on this one so that you can see how it kind of works. So let's say maybe you want to find the Laplace transform. Let me do something simple. The Laplace transform now of e minus 2t, right? Cos 3t. Okay, this is kinda okay. So let's look at this one. So we know. So this is the f of t, right? And then this is the exponential, isn't it? So basically what we want to do, we know that the Laplace transform of cos 3t, Laplace transform of cos 3t using this is going to be what? Is going to be, for this one is going to be s over s squared, right, minus omega is what? Is 3, so 3 squared, isn't it? That's how it's going to be if it's just cos 3t, right? But now we are introducing e to the power 2 minus 2t. So what are we going to do? Where there is s here, we need to shift by these constants here. So that's why here we are going to have s, where this s, let me just put bracket, this is 3 squared. Where this s, let me just put bracket. So remember I said if s is positive here, it's going to be s minus a. If s is negative, this is going to be positive. So here if a is negative, so this is going to be positive. If a is positive, this is going to be negative. So now coming back to this one. So here we have negative 2, right? So you see we are supposed to have s here. But since it's the first shifting theorem, it's going to be s minus, right, minus negative 2, which is going to be plus 2. That's why you are getting the positive, because it's minus. This is 2, right? Same thing here, s plus 2. And remember, this one is squared according to the Laplace transform for this hyperbolic function. So this is how you can evaluate the Laplace transform of e minus 2t cos 3t. So this is going to be s, okay, let me remove the bracket with it, s plus 2 squared minus 3 squared. So that's it. this is it. So again, let me look at another one. Let's say probably you have the Laplace. You wanna find, you have the Laplace, let's say you have t, right? We know what is the Laplace of t, isn't it? We know what is the Laplace of t based on our derivations, isn't it? Okay, this is from the first video. So we know what is the Laplace of t, right? It's 1 over s squared, because remember, this is 1, so it's 1 factorial over 1 plus 1, so it's 1. So it's going to be s squared. So this is s squared. Okay, so now let's say we wanna use the shift. If you are using the shifting theorem, you'll be given something maybe e to the power, let's say this, let me just use another value, 4t, right, and then t. So find this Laplace. So here, you know, this is my f of t, right? This is my f of t, then this is going to be e at. So if you have this format and you're finding the Laplace of this format, always if you're finding the Laplace of this format, the first shifting theorem. So but then you start with evaluating the Laplace transform of the function f of t, because that's the one that is going to give you direction. We know that this is 1 over, where this s, I put brackets, just going to put bracket, this is squared. So and then you come and look at the value of a. The value of a is what? Is positive, so which means it's going to be s minus a positive value, which is 4, right? So this is it. So that's how you evaluate the Laplace of the Laplace of e to the power 4t t is just going to be 1 over s minus 4 squared, according to the first shifting theorem. So this first shifting theorem is important because it's going to allow us to add even more onto what we have done. So now, what if we have when I continue to evaluate different types of functions. So now we're gonna find the Laplace transform of EAT, right, cos omega t. So how do you evaluate this one? Instead of using integration, that is going to be lengthy, so now we can just use the first shifting theorem to evaluate this Laplace. So again, remember, we said you look at the f of t function. We know that the Laplace of cos, is what? It's s over s squared plus omega squared, isn't it? But then now we are shifting s by a. A is positive, so where there is a s here, it's just going to be s plus a. Sorry, it's going to be s minus, because it's positive here, so we are going to subtract it. So this is going to be s minus a. This is going to be s minus a squared, right? So this is how you evaluate the Laplace transform of this expression of an exponential and a trigonometric. Same thing with the Laplace transform of sine omega t. It's going to be, remember, for sine we have omega over s squared plus omega squared, right? So we are shifting by positive a. So where there is s, we are going to have s minus a squared. So again, this is what you have. So now we have done all of them, all of the ones that we're going to need. So we looked at t to the power n. We said this is n factorial, s to the power n plus 1. We looked at an exponential, which we deduced to be 1 over s minus a. We looked at trigonometric, sine a, or or let me just omega, right? A and omega are real constant. For sine, we said this is going to be omega, right? S squared plus omega squared. And then the Laplace transform of cos, of cos omega t, this is going to be s over s squared plus omega t, or omega squared. Again, if you know one of these, you can easily derive the other because the same denominator, you swap the numerator. So the omega, the Laplace of hyperbolic functions cos at, we said this is what the Laplace of cos a squared minus a squared, and then obviously if you know this one, same denominator, right? And then you can just easily find for sine, this is going to be a over a squared minus a squared, right? And then now we have just introduced 2 using the first shifting theorem. We just introduced this one, these 2 using the first shifting theorem. So if you have cos w, right, so this is going to be what? Cos omega, this is going to be s minus a over s minus a squared plus omega squared. So the Laplace transform of EAT sine omega t is going to be what? It's going to be omega over s minus a squared plus omega squared. So these are very important. You have to remember all of these because you'll be applying these to solve problems, to work through complex problems, simplifying them, transforming them. So I highly advise you to take note of this, since we'll be working on this. So now let's say, let me just do an example. So let's say it's a question, find the Laplace transform. Find the Laplace transform. The Laplace transform. Find the Laplace transform of f of t is equals to probably t squared minus 3 squared. So we're gonna find the Laplace transform of this. So how can you find the Laplace transform of this? First of all, t squared minus 3, you can expand this towards to t to the power 4 minus 6t squared, right, plus 9, isn't it? And then now we want to find the Laplace transform of f of t, right, which is equal to the Laplace transform of t squared minus 3 squared, right? And then we have expanded this, so this is the same thing as the Laplace transform of t squared minus 6t squared plus 9, right? And then using the linearity property, this is going to be minus 6 the Laplace transform of t, no, this is t to the power 4, yes, t to the power 4, and then this is t squared plus the Laplace transform, or just factor out 9, the Laplace transform of 1, right? And we know all of this. This is going to be 4 factorial over s, 4 plus 1 is 5, this is to the power 5 minus 6 times the Laplace, so this is going to be 2 factorial over s cubed plus 9 over s, right, because the Laplace of 1 is 1 over s. So this is what you get, isn't it? And then you can just simplify this. This is going to be 24 over s to the power 5 minus 12 over s cubed plus 9 over s. So you have transformed this function from t to this format using the Laplace transform. So this is just a basic idea of the Laplace transform. In the next video, we are going to look at the inverse of a Laplace transform, which is a very important concept.